Thank you for joining us with GG413 Geological Data Analysis. I'm Garrett Apuzen-Ito at the University of Hawaii. This series of videos will continue our discussion of hypothesis testing, and in particular section 2.2 on parametric tests. This video in particular will start our discussion of the chi-squared goodness of fit tests. But before we get into that, let's talk about some general aspects of chi-squared. So if we have a variable, and we'll call this variable gamma, and we have a collection of this variable, and again, this variable can be anything. It can be a z-value, it could be data, it could be anything, just so long as they are independent and normally distributed. So if we have any variable, a collection of variables that are independent and normally distributed, then the sum over all new independent variables, this is the Greek letter nu, there are new independent variables. If we sum the squares of those variables, then the distribution of the sum will be chi-squared. So that's a real sort of a basic definition or a basic way of understanding where the chi-squared distribution comes from. So let's go back to our situation, our particular case of our standard deviation. Or our variance. So recall that the variance of a sample is equal to the sum, I'll use I, not J, of all the measurements in the sample of the deviation from the mean squared divided by n minus 1. Okay? So you can see that if xi is normally distributed, and that would be the tendency or the case if the sampled population were so. Then you can see the similarity of this equation with the equation I just wrote on to describe the sum of squares of our independent normally distributed variable gamma. So that looks very similar, right? So this is why, so s squared, okay, is indeed a sum of nu, and in this case equals n minus 1 independent variables that are normally distributed. And that is why s squared has a chi-squared n minus 1 distribution, as you were told last week. We haven't told you why it is, but we just told you that if you repeatedly made samples, the variance will have a chi-square distribution, and this is generally why. Let me finish writing. What I said. Okay, so that's why S, the variance, has a chi-square distribution. Let's look at another application. Say we sample pairs of data, and they could have any variable name, but let's just for now, let's say we measure X and we also measure a corresponding value T. Okay, they could be X and Y, or I don't know, Z versus L, but let's call them X versus T. And if we plotted X versus T, suppose they vary together some way. Okay, and we may have theory or knowledge from previous studies that on average the mean value of X versus T follows some sort of curve, some sort of mean, or some sort of curve or function. And so we might sketch the curve as such. So the curve describes how the mean value of X is expected or may vary with T. So we may ask the question, do our data follow mu T? Or perhaps more formally, does the population that we've sampled also have a similar dependence between X and T? So to answer that question, we could define a statistic, a misfit statistic, say xi minus mu of T, and let's normalize by the standard deviation. Now let's look at what the standard deviation is. So you can imagine that in nature, if our if our sampled population really does behave like this theory predicts, then we would expect scatter about that point, but at any one measurement need not necessarily lie along this point, as you can see as I've sketched these data points here. So at any given value of T, there's going to be some variation in X about the mean. Okay, and so it makes sense that if we're going to contrast X with the mean value, we should compare that to a measure of the variation expected due to other processes. So there's a natural variability due to some noise or noise. Okay, and again, noise could be some natural process that's just not explained by this theory, but it's there, and it's a natural occurrence. So that we don't expect every point to lie along this line unless, of course, the system is very simple. we expect it to vary, so we can measure the goodness of fit of our data to this theoretical curve, and by taking that difference and normalizing it by that average natural variability. So if we take the sum of all our normalized deviations over all of our points, then, and if this noise is Gaussian, is normal, then that sum will be a chi-squared distribution of n minus 1. And if the noise, okay, that's true. Again, if the noise is normal. So if in fact our sampled population is heavily influenced by the process described by this curve, okay, let me write that down. If it does follow our theoretical curve, what's our sort of most probable value of z? Most likely the z values will be less than or equal to 1, about 68% of them. Okay? Or in other words, the corresponding of chi-squared should be about n minus 1, if that's the case. So one way to statistically test whether our sampled population is heavily influenced by this curve is we could calculate our chi-squared variable and compare with our critical values, our critical value or critical values, and a critical value for chi-squared, for example, would be based on our significance level and number of degrees of freedom. So that's a second application of using chi-square statistics to do some hypothesis testing. So the next example I'm going to show will be very much like this last example, but the curve that we're going to compare with, this theoretical curve, will be a probability distribution function.